is from Mark Kulaczewski from videantis on a software approach for easing embedded acceleration of OpenCV applications. Mark is VP of System Integration and a co-founder at videantis. He's responsible for all system integration aspects of videantis's IP into customer designs, including both hardware and software integration, and for customer project management. Mark has 20 years of experience in the field of hardware and software engineering for parallel, heterogeneous, multiprocessor architectures, and he holds a Master of Science degree in electrical engineering from my alma mater, Purdue University.
Okay, let's see. Thank you for the introduction, Brian. Thanks for having me here for my talk, A Software Approach for Easing Embedded Acceleration of OpenCV Applications. My previous speaker have put some light on different aspects of how embedded vision systems can be implemented. And I would like to add another aspect for that. But before I start to do this, I need to talk a little bit about videantis itself. We are one of the smaller players compared to my previous speakers. So I'll spend a few words on who videantis is. We are a one-stop solution provider for multi-standard video and vision processing. What we do actually is we license IP. We license a programmable multiprocessor video DSP IP. And in addition to that, we offer optimized, pre-verified applications and optimized libraries for certain application domains. Especially for embedded vision is our offering that we have an embedded OpenCV acceleration with a combined hardware-software approach. Basically means we have an optimized OpenCV library that does some of the processing on our IP. We actually had our first licensee for this product more than 2.5 years ago, so we have been doing things in that domain for quite some time, and with this talk I just want to spend some light on our lessons learned and why we do things the way we do them. The benefits for embedded vision, if you follow an approach like we do, is on one hand, we can show that there are significant cost reduction through a unified platform approach. We can see significant performance gains for an accelerator like this, and we have significant reductions in power consumptions, and I'll give some numbers for that. Furthermore, what's important for the embedded vision domain, the functional upgradability over product lifetime. We have an evolving area of different algorithms, and things change basically by the minute, and it's vastly important to adapt to that. So, my speakers have already talked about a few of the aspects. So what is it about embedded vision? And I want to point out the term embedded. So embedded vision in general, vision processing in general means we have applications that are extremely performance hungry because we have to deal with a lot of data that needs to be processed. We require flexibility due to the varying algorithms. For embedded, we have some additional constraints. We have usually low-cost, small silicon size constraints. We have tight power consumption limits for portable devices. And we have constrained memory interfaces and memory sizes. So the question is here, how can we bridge the gap from general vision processing to embedded vision processing? What people currently do is they basically use all available resources that there are on an SoC. So they use the CPU, the GPU, the DSP in some way. There's no really official way of doing it. What is also emerging, and you will hear in the following also several talks about this, are programmable accelerators. They might be hardware programmable, like Jose explained to you. They might be hardwired blocks, like Mario talked about. And we have vision DSPs, and this is my topic. So if we look a little bit at the software landscape for embedded vision, we see that there is a software support for acceleration is expanding rapidly. We can see that OpenCV is widely adopted in the PC domain, but usually for embedded platforms, it's too performance hungry. So if we look at what currently manufacturers offer on embedded platforms, we can see two things. One is proprietary libraries, or basically adapted standard libraries. Just to name a few to illustrate how this field is expanding, we have the proprietary offers like TI's VLib, Qualcomm's FastCV. We have the activities by NVIDIA for their Android OpenCV on Tegra devices. Just recently, they announced that for Tegra 5, they will also include programmable GPUs. We have CEVA DSP's CEVA CV. I just recently read a press release by Renesas for their automotive ARCAR H2 series, where they announce OpenCV support for that platform, and we have something that we do. So there's a huge variety of accelerating hardware and supporting APIs, and the question is here, what can we do to ease the porting of native OpenCV applications to embedded environments? And with native CV applications, I mean applications that rely on the OpenCV API. Of course, you can write all applications in straight C, but this is what we're talking about here. Let's go one step back and let's have a look at the hardware basics for embedded vision acceleration. Almost all architectures that you see these days share the following. You have some kind of multi-core CPU with or without vector processing extensions like the ARM Neon things. We usually have a unified shared memory, and that's a big difference compared to the PC domain, for example. We have GPUs with a varying degree of flexibility, and what's now showing up are accelerators, programmable logic, or vision processing DSPs. So how can we integrate these accelerators into OpenCV? Our decision to lower the bar for application programmers was to stick to the original OpenCV API as much as possible, so no proprietary API. What we actually did was that we do the accelerator constraints checking and invocation under the hood hidden by the API. The application programmer only sees the OpenCV API, and all technicalities about how the accelerator is accessed are hidden in the optimized library. With constraints checking, I mean that usually on programmable accelerators, you only support a subset of the operations that OpenCV can do. So for example, you have limitations on the data types that you support. You have limitations for some image dimensions or things like that. By doing it this way, we always have the CPU version as the functional fallback. So you start with taking your code, dump it onto the host CPU, and it'll run immediately. It will not get the performance that you expect, but it'll run, and you can start from there. Memory allocation is a very crucial matter for implementing programmable accelerators. Why is that so? We always have to deal with high bandwidth raw image data. For CPUs, and the way they use memory, it's a virtual memory system, so your data is spread out somewhere over the physical memory. Whereas accelerators mostly use physical memory addressing. So we need to find a common ground to exchange data between these two entities. Otherwise, we have to deal with extensive memory copy operations, and you don't want to do it in an embedded world. So what we did is we added special memory allocators for these shared memory regions. So basically, we have one region that gives you, if you allocate a region of memory, a physically contiguous memory. And that means that you can exchange data there between the CPU and the allocator, while at the same time also accessing this memory in a cached way from the CPU. The accelerator use logic that we hide within the OpenCV library is then rather simple. So for each function call that someone does in OpenCV, we first of all check, well, do we support this specific operation at all? As I said, there are limitations on what is usually supported on an accelerator. So if it's not supported, then of course we have to do it on a CPU. This is our fallback. If it is supported, we need to check, well, where is actually the source and where is the memory region for the result data? And if this is in a specific memory region that is physically addressable, we can do the processing on the accelerator. All this is hidden in the OpenCV API. I'm going to use the following example just to shed some light on how this is now used in porting an application to an embedded system. So what we do is we use the CV block color block detection application. This is actually an OpenCV library, and in addition to that, an application. So what it basically does is, like illustrated in the images below, is we find regions with a certain color in an image, and then we track the regions across images. The source code, you can basically download it from there if you want to look into that. I would also put some numbers to implementing this on a specific platform and not doing it in general, because only if you talk about power, you need to talk about a specific platform. So the platform we used is basically, on one hand, an ARM v5 1.2 gigahertz processor, and attached to that is one of our accelerators. So in order to give you an idea what this IP is capable of, it can basically perform up to 192 simultaneous 16-bit pixel operations. You don't have to use all of that, but it can if you need to. This whole system is rather small, and it is also very attractive from a power consumption point of view. But I'll come to that later when we do some comparisons. Now let's go back to the algorithm. If you look a little bit more into the details of the algorithm for this color blob, you'll see that it's the classical partition of a lower level processing that Mario already introduced and the higher level symbolic level processing. So we have color conversion into a different color space. We have some multi-channel image thresholding there. We have morphology operators that are being applied. And then we have the actual labeling and the blob detection and tracking. So if you just download the code, dump it onto the ARM processor, what you get is roughly 11 FPS. And now let's think about what do we need to do this is actually for VGA resolution, to get this above the 30 FPS real-time constraint. So for all these accelerators, of course, all this low-level processing is a very good candidate for all the acceleration. So in order to really activate the processing on the accelerator, all you need to do in this flow is to make sure that the data that is being processed and the results area for your processed data is placed in this specific memory region. And the only difference you have here is that you have a new memory allocator. So instead of a CV create data, you have a CV create data, and we call it overlay. That's the only difference in the code. The rest is being taken care of under the hood. Now, if you do these changes and allocate the memory regions for color conversion, the thresholding, and the morphology in this specific area, then the accelerator use logic activates the actual processing. And for the initial speed up, we also decided to leave the labeling, for example, and the blob detection and tracking. This is symbolic data processing anyway on the ARM processor. So if we do it like that, what do we get? If we look at the performance without acceleration, we started with these roughly 11 FPS. Now, if we use just one of the video processing cores of the videantis IP, you get initially an acceleration to 32 FPS. The speed up there is, of course, different for different code sections. We see that we get, in this specific setup, an acceleration of 5 times on the accelerated code, with just changing a few lines of code. And since there is still a section of the code that is processed in a sequential way, the overall speed up is roughly 3. But it's enough to save the day in this instance. The total power efficiency, if you do the numbers, increases by a factor of 6. So we are 6 times more power efficient now than we were before. Why is that so? Well, this architecture is more power efficient in doing this low-level processing. And we take off a significant load of the ARM. So we need fewer cycles on the ARM, and we need less power per cycle on the accelerator. So what are the advantages of this flow? We start with legacy desktop-developed applications and compile them out of the box. We can use an iterative refinement by figuring out, well, I want this on the accelerator, now I keep this on the ARM. And this is possible with this flow. And what's also possible is that existing applications benefit from newer versions of the accelerated library. For example, when new functionality becomes available on the accelerator, then it's used basically under the hood. So this is really a simple flow for porting vision applications to embedded environments. So this was the acceleration and some power analysis for this specific platform and this specific application. I would also like on the next slide to do some additional comparisons just to give you an idea what is possible today with programmable video DSPs as accelerators for OpenCV. And what we did just to illustrate that is you can download from the Google Play Store the NVIDIA OpenCV demo suite, which is a bunch of little OpenCV applications, and NVIDIA also provides an optimized version for that. So you can see, well, what is the performance I get if I run this application on a straightforward Cortex-A9, and then what do I get if I optimize this? You can already see that through optimization, you have a performance gain between 2 to 10, depending on the application, depending whether it's only neon that is being used or if even the GPU is involved. Now, if you do the processing on a programmable video DSP accelerator, you get another significant speed up because these architectures just have an instruction set that is highly tailored towards processing data like that. So if we compare it to the baseline version, so basically compiled out of the box, you get another performance boost by a factor of 100. And this is just basically counting the processing time. If we look at power efficiency, it gets even more dramatic because now it comes into play that architectures like these optimized video DSPs are just more power efficient. There are usually no caches in there, which burn a lot of power for video processing, for example. Now, if you do the numbers here and compare it against a Tegra 3 baseline implementation, you actually see that if you look at core processing power, you have a difference by a factor of 1,000. And this is technology that's available today. So in conclusion, we currently see that accelerators are increasingly used in emerging SoC architectures to enable that vision applications are really possible on embedded architectures. So the software integration of these accelerators is a crucial part to ease the transition for programmers. And the way we did it, and this has been well received by our customers, is by adding special memory allocators, which give a clear understanding about what you need to do in order to have something processed on an accelerator. And this results in very simple decisions for accelerator use. We see that an initial acceleration of applications is quickly achievable, and you have the option for an iterative refinement later on. And last but not least, with these optimized vision accelerators, we already have today speed-ups beyond a factor of 100, and power efficiency increases by a factor of 1,000. You can see this demo application also on our little demo table next door, so I'll be pleased to welcome all of you there. I've added some more resources that explains a little bit how we do the OpenCV processing. Thank you for your attention for now, and I'll be happy to answer questions. Sorry.
Is it working?
Yes.
You said that you are tracking like red color sections so that you can immediately, on the next frame, zoom in on that.
Yeah.
What happens if there is a glare on that, let's say if it is a shiny red surface? Do you track 2 or 3 such sections so that you can if one section goes blind, you can use the other section?
Okay, that actually goes into the detail of the algorithm itself, which is which is not ours. But as far as I know, the algorithm takes into account the size of regions that are being tracked and tries to basically re-identify things that disappeared for some time and then come back into the image. So it can take care of that. But the problem you mentioned is probably an issue of, well, how robust is your color detection? And of course, glare is a significant issue. And I would actually have to check what the algorithm there is really capable of doing.
But if the algorithm can track 2 or 3 such regions,
Yeah.
then even if one is lost, it can use the other 2 for getting the bearings. If let's say you use a blue section or a red section and a yellow section, or 3 reds, but then you can identify even if one goes out of view due to glare, you can always use one of the other 2 for getting your bearings once again on a new frame. And you don't have to wait for the first one to go out of glare and come back into focus.
No, there is some logic built in that tries to take that into account. But of course, these algorithms always have limitations. So what you can handle and what you can't.
Any other questions?
Johannes Stahler, Mr. Synopsys. Can you sketch in 1 minute what software development environment looks like for your combined ARM plus accelerator solution?
Okay, so what we offer, what we provide to our customers is basically an OpenCV library. That's basically the standard OpenCV library that is changed in a few places. And below that, there is basically a system implemented that basically makes sure that the accelerator firmware is called for these specific functions. So for the application developer, except for the memory allocation function that I already mentioned, it looks like a regular OpenCV library. There's no difference, because he does not write the code that runs on our accelerator. That is delivered to the customer in a pre-optimized way. So it's really a library approach. And there's another down there. In the back.
Enric Schubert,
okay.
Missing Link Electronics. So when we started to take the Open Computer Vision library apart, we found 2 things. First of all, it was pretty much invented with a CPU architecture in mind. And when we started to accelerate things, we saw that sometimes you have to leave the original algorithm behind and use concepts like tiling in order to get really good accelerations beyond the factor 1000. So what are your visions, your roadmap in taking some of the more complex parts of Open Computer Vision and accelerate them?
Yeah, of course you can imagine that we have a multi-core architecture. So in order to process algorithms of the type that I mentioned on a multi-core with data tiling and things like that in a parallel way, you need to basically leave the original path of the algorithm anyway, because your algorithm is different. So of course our criterion for acceptance is it needs to be binary compatible. So we need to have the same output in our implementation compared to the original OpenCV. Now, if we talk about other OpenCV functions, like we also have a face detection demo, for example. This face detection is basically a huge monolithic block of C code that has been integrated into OpenCV by putting basically an API call in front of that. So under the hood, it's not really OpenCV. And for that, what we actually do for key API functions, we actually implement an equivalent version on our IP. So we, for example, did also the face detection, but under the hood, it is really different. There is not really a similarity with the original algorithm. It gives you the same result, yes, but it's under the hood, it's done in a completely different way. And this is really necessary, otherwise you won't achieve the speedups.
How do you convert the software concept then into hardware? Use high-level synthesis, like the previous speaker indicated?
No, since we have a programmable DSP, so it's basically going from one C code description to another description in a programming language. So for our course, the actual development environment is a mixture of C compiler and, for optimization purposes, assembly code. So it's basically a mixture of both. There is no automated flow going from an arbitrary C code to a parallel optimized version running on our course. I guess we could be making a lot of money if we have a flow like that.
Any other questions?
Hi, Adar from SIVA. I wonder if you can talk about the bandwidth constraint.
The bandwidth constraints, there of course what comes into play is what does your architecture, so basically your core architecture look like specifically. If we talk about bandwidth in our architecture, just to give you some additional information for that, each of our cores has an own DMA unit. So we have for the 8-core vision subsystem, we have 8 DMA units that can access data from external memory autonomously and write it back autonomously. This is completely controlled by the firmware running on each core. And for some applications, we have the same firmware running on all the cores. For other applications, we have different firmware on each of the cores running. So the bandwidth is basically handled by this DMA unit that is attached to each of the cores.
So for every OpenCV function, you would load the data inside, do your processing, and write out to the external memory, or do you optimize this?
Yes, the handover point is basically the external memory region that I talked about. So if you have a handover from some data that you have accessed on the ARM, and then you go to the accelerator. The handover point is this shared memory that I talked about. So basically, input is we read the data from external memory, and we write it to external memory. For some OpenCV functions, so for some basically macro functions, you of course also have a way to provide optimized firmware by combining certain of the function calls that are used under the hood. So for example, like a Kenny operator. A Kenny operator under the hood, as Mario explained, it does some Gauss filtering, it does some Sobel and so on. And if you do this again and again, we provide optimized firmware for that where you do not have to write out all the intermediate data. This is done in one step on the core. And you only access the data once, and you write out the result once.
Thank you.
Do you distribute the soft versions of your code? Something like do you distribute RTL code for your processors, or it's only hard processors?
No, as an IP provider, we license the RTL of the processor.
Oh, you do? Okay.
Yeah.
Thank you.